So go. What do you want to
So
talk about?
I was confused about a few things with the parametrizing when it comes to using Stokes theorem. So there's a few exercises where you have to change things into in terms of r and theta.
Mm-hmm.
But remember how we used to say x is equal to r cosine of theta, and
Mm-hmm.
then when we plug it into the integral, we put it as r into d theta and dr.
Yep.
So when I couldn't figure out why it wouldn't work for me, I looked up the answers online and they just completely disregard the r's, even in the integrals.
What problem are you talking about?
So, particular one would be like exercise number 2, I think. It was page, I do not remember, but it
In what
was 16,
section?
it was 16.8 Stokes theorem.
Okay, so exercise number 2.
Yeah.
F of x, y, z is x squared sine z I plus y squared j plus x y k. S is the part of the paraboloid z equals 1 minus x squared minus y squared. That lies above the xy plane, oriented upward. So we're going to evaluate curl of f dot ds. Kind of glary. Okay, that's better. Okay, so this is 16.8, number 2. What do we want to do first? What does Stokes' theorem say? First, let's draw a picture of this, I guess. What does it look like? So we have all these nice tools. You can draw this.
Professor, are you recording this by chance?
Yep. So it looks like this. Imagine we're cutting off at 0 here. And so it's just like this upside down dome. And the normal vector is pointed upwards. Excuse me. So what do we want to do if we're going to use Stokes' theorem?
We have to equate it to the line integral of f dot dr.
Okay, but what do we need to deal with the line integral? We need to find a curve that is its boundary, right? Yeah. So we got to find a boundary. What do you think the boundary is going to look like?
Well, it's going to be the curve that's cut by the plane into the paraboloid.
Yep. What does it look like?
Like some kind of circle.
It's a circle.
Yeah.
Right? So the curve the boundary curve is given when z equals 0. That is 0 equals 1 minus x squared minus y squared. So the boundary curve is x squared plus y squared equals 1. Right? We have let's turn the cameras on, everybody. We have a circle of radius 1. What orientation do we have? Is the next question. So if we look at
It's upward.
the surface is oriented upward, correct. But now we have a curve. What's the orientation on the curve? So I can draw a plane like this. This is my curve. That's the boundary. I imagine my little dome sitting right here. Which way does my curve go?
Counterclockwise.
Counterclockwise. Why counterclockwise?
I just put some data points in. I don't know what else you need to do.
How did you put data points in here?
Like for X and Y, I kind of just guessed it, kind of.
So given this equation, x squared y squared equals 1, there's no notion of direction or no notion of time. No matter whatever way you put points in, it's not going to tell you which way the orientation of the curve is going. The way you determine that is the orientation of the surface is going upwards, right? So we're going to use our right-hand rule that tells us how the surface is oriented. If our curve is going this way, our thumb points up, which matches the orientation of the surface, right? If we were going the other way, our thumb would point down, which does not match the orientation of the surface. Does that make sense?
One question. When we talk about flux, is the curve still like the hand and the surface still the thumb?
When we talk about flux, has nothing to do with the right-hand rule, right? The right-hand rule has to do with orientation, and flux is some number of things going through a surface. So no matter what we're talking about, any kind of integral, any kind of line integral, any kind of object, if we're talking about orientation and which way it is oriented, we're going to use the right-hand rule, and it's still the exact same rule. Fingers point towards the other objects, and the thumb is the orientation.
Okay.
So since we're dealing with this orientation of this curve, we need to make sure the orientation of the curve matches the orientation of the surface. If it's going counterclockwise, it matches. If it's going clockwise, it does not. Okay? So be very careful about your orientation on your curves when you use Stokes' theorem, because you will get negative answers if you have the wrong orientation. Okay? So you got this nice curve, C. What's a parameterization of this curve? How do I parameterize the circle, the unit circle of radius 1 going counterclockwise?
So you say x is equal to r cosine of theta. That's what I would have said.
Well, we're talking about t here, but this is a parameterization of this thing. So just, okay, so cosine of t. And what is r here?
Okay.
What does r mean? R is the radius of my circle. What is the radius of my circle here?
1.
1. So this is an appropriate parameterization of the circle of radius 1 moving in the counterclockwise direction.
Okay.
I don't need an r or anything like that because r is 1.
Oh, okay, that makes sense.
Okay, so this is my curve. And what does Stokes' theorem say? Stokes' theorem says that this integral is equal to the integral over my curve of my vector field dot dr. Right? Okay. Any questions? Yes? No? So now what do? We're going to compute this by computing this. We already know f, and we just need to compute the dr. F, which is, this is equal to f on r of t, dotted with r prime of t, dr. Right, this is from 16.2. We don't need a fancy thing for that. Okay. So what do I do next?
Find the values for r prime, and then compute, I guess.
Yeah. So let's get to doing it. What's r prime?
Sine of t minus cosine of t. That's it, I guess. Or is it
I think
minus
it's
sine of
minus
t?
sine cosine of t.
Minus cosine. Yeah.
Yeah.
That's true.
Okay. So now I'm evaluating f at these points. So tell me what I should be writing here. The integral from where to where?
Let's see. So from minus pi to pi, or 0 to 2 pi.
Okay.
Oh, I
Which one
guess
do you
in
want to
this
do?
case, any one of both works. So 0 to 2 pi, I guess.
0 to 2 pi. They both work. So pick whichever one you want. What goes here now?
F, but in terms of r of t, so instead of x squared sine something, we're gonna write cosine square of t times cosine t.
Cosine t. How did you get a cosine t here?
Actually, no, I said minus sine t. Sorry.
There's a minus sine t here. So this is correct here. We got x squared. That's cosine. And this is a sine of z,
Sine, yeah, sine
right?
z.
And what is z? Z is 1 minus x squared minus y squared.
Yeah.
Right. So z is 1 minus cosine squared minus sine squared. Right?
Yeah.
Which is
Yeah.
0.
True.
Right? So what's sine of 0?
0.
0. So we'll put this here. We'll keep that there for now. This is 0. Plus, what does this one say?
Y squared would be sine t. Yeah. Sine t
Sine t
squared.
squared, j, plus
Cosine t sine t.
okay. Right. I made a slight error here because we forgot one thing. This is a curve in 2 space, right? But our
Okay.
surface lives in 3 space, right? So how do we parameterize this same curve in 3 space? Because this is a 3-dimensional vector right here. We use a
Sure.
dot product with another 3-dimensional vector, right? What
Sure.
3-dimensional vector describes this curve?
Oh, you just have to add 0, I guess.
Exactly. Just add 0 for the k component. Right? So I take this, I dot it with the vector cosine of t, no, sorry, minus sine of t, cosine of t, and 0 dt. And so what do I get? The I components are 0, because this is 0. The j components are sine squared t, cosine of t. And the k components are 0 dt, 0 to 2 pi. Right? And then we integrate this. Okay. For the final, if you get something like this, you can literally just say I put it in the computer. Since you have access to a computer, you can literally put this in the computer and it'll give you a number. Right? I put this in the computer. I don't care. Excuse me?
That's cool. Yep.
Yeah, I don't care if you can integrate this. You should be able to. I am silently judging you if you can't, but I'm not grading you if you can't.
I have a question.
Yep.
So when we say f is a function of rt times r prime of t,
Dot.
that dot r prime of t, that only means that we have to write f in terms of t though? We don't have to consider the prime or anything like that?
Let's look at just this part right here. F of r of t. So think about this vector field. The vector field is everywhere in all of 3 space, right? There's vectors everywhere, right? But I'm only really interested in where the vectors are on my curve, right? Because if I'm studying just this curve and how the vector field affects this curve, I don't care what the vector field is up here, right? That's what this part of the equation means. It says, look at where f is on my curve.
Okay. Yeah.
Right? That's what this symbol means right here. Right? The dot product then says, okay, let's back up here. This is f on my curve. This is the direction my curve is moving. Right?
Oh. Yeah.
That's what the derivative says. The derivative of your parameterized curve is the direction the curve is moving. Correct? So this dot product then means this is the amount of my vector field that's in the same direction as my curve moving.
Okay.
Okay? And then I'm adding that up. And that's telling me how much the vector field is affecting movement on my curve.
Gotcha. But when I get the concept behind it, but mathematically when we write it down, where is the r prime?
R
Like,
prime
how
is right here. This is R prime. It's the second vector.
Oh, okay,
Right.
you're dotting. Okay,
I'm
yeah,
dotting
you're
it. This is the dot product up here.
right. Gotcha. All right.
So compute this. You should be able to compute that, but it's time consuming and the computer is a lot faster and you have one, so use it. You should use the computer now and tell me what this number is. If you do use the computer or something to compute your integral, please say I use the computer here.
Okay.
Okay.
I got 0 when I did this in the homework.
Okay.
Like I did u sub, then like u squared du with the bounds from 0 to 0, and that's 0.
Yeah, that sounds reasonable. We can compute this. We can draw a picture too. I bet you if we draw a picture, this will be 0. Y equals sine t squared cosine t from 0 to 2 pi. So what's 2 pi? That's over here. That seems like 0, right? This blob cancels this blob, and this blob cancels that blob. So we should get 0. Any of those answers is a reasonable one. You could literally draw this on the computer, sketch a picture, and say, I drew this on the computer, I got 0. Or I integrated this on the computer, and I got 0. Right? Any questions?
Just one. So the reason the R is not put in is because we know the value and it's 1.
Well, we didn't do a polar coordinate change either.
So yeah, that's what I'm confused about. Like,
We did
how do you know
not
when you're
do a
doing
change
that?
into polar coordinates at all.
Okay, but how do you know when you're using polar coordinates or when you're, I don't know what this is, but when you're doing that?
This is just, if you're going to do a line integral,
Yeah.
it's only got one variable in it, t, right?
Okay.
So there's no way we can change in the polar coordinates, which requires 2 variables, r and thetas,
True.
right?
True. Yeah.
Line integrals have one variable, one parameter. If I was doing a surface integral, I could make a change in the polar coordinates because that has 2 variables, but we don't have one of those here. Okay?
So if it was the other way around, where we would have to find the
If
curl of,
yes, so if I wanted to compute this directly,
yeah.
where I'm doing a surface integral, I may need to do polar coordinates, possibly. I can't promise that. But why would I compute this surface integral when I can compute a line integral,
Gotcha. Yeah.
right?
Makes sense.
Okay. Any questions? So let's think about this in a different light. What does this tell us? This is a curve that's closed and simple. What kind of things do we know about vector fields like this?
They're conservative?
Well,
Yeah.
no, but that's the right idea. If a vector field is conservative, the integral over any closed loop is 0. Right? So
Okay.
instead of doing this, which is not that hard, we could do this. We could also check to see if this is a conservative vector field.
So we just do the curl of F?
No. The curl of F is not what we're looking at here.
I mean, if you want to check if something is conservative, you do the curl equals to 0, right?
In two, so I see the difficulty here. That is correct in higher dimensions, right? In 3 dimensions, that's a perfectly reasonable way to do it. But the vector field that we're integrating right here isn't really in 3 dimensions,
Okay.
right? Because this thing is 0 right here. Correct?
Sure.
So we need to jump between 3 dimensions and 2 dimensions. Technically, this is in 3 dimensions, but we need to compute the curl of this thing right here, right? With 0 in its place.
Okay.
Okay. And if we compute that to have the curl equal 0, then it's conservative.
Okay.
Right. So and then we can just say this is 0. That's great. So we have to make a slightly different adjustment. And we're not computing the curl of this f, we're computing the curl of this f.
Okay.
Right?
Gotcha.
Does that make sense?
Yeah, because of the change in dimensions.
Yeah, because we're integrating now. This integral is the integral over the curve, not over the surface. Right? And the vector field on the curve is this one with the 0 component in the I.
Okay. Gotcha.
Okay. Okay. Did that make sense? That's a complicated question, but it illustrates the important things that have to go into Stokes' theorem. So let's take a recap of what we did. So we were told we wanted to use Stokes' theorem, right?
Mm-hmm.
What did we do? We found the boundary curve. I'm going to go write this down. Plan. Find the boundary curve. Okay. This is going to have lots of small steps, right? Because we did lots and lots of small steps without really thinking about it, right? So we found the boundary curve. That's what this circle was, right?
Yeah.
We oriented the boundary curve? Correctly. How do we do that? We made sure the orientation of the curve matched the orientation of the surface. Correct? Parameterize boundary curve.
I have a question.
Yep.
When it came to the orientation, could you go over how you did that real quick? Just like knowing which direction it goes.
Yeah, so what does this say here? It says the surface is oriented upwards, right? So imagine this picture is, I have this little dome. I actually have this already up, so I don't have to like show you my hand. This is our surface right here, right? And the normal vector is pointed up right here, right? And our curve is this curve right here, right?
That's the projection.
Well, this is where this is the boundary curve. I'm not projecting this. I'm not projecting the surface at all. Because if I project the surface, then I fill in all this extra stuff in the center, right? Which is not what I'm doing. I'm only seeing where the curve, the boundary of the curve is, which is when z is equal to 0, right? When z is equal to 0, I get exactly this. Okay?
Oh. Question.
Yes.
So, do we always consider that 0 is equal to 0? Z is equal to 0, sorry.
No, I'll answer that right after I talk about orientation. That's the next question of interest. Okay. And so here, I know my surface is up here and it's pointing up, right? So I'm using the right-hand rule to tell me that, to make sure that the orientation of my curve and the orientation of my surface match up, right? So if my curve was oriented this way, that would mean that my fingers point towards my curve, my thumb points the orientation of the surface. And where's my thumb pointing, Nick? My thumb is pointing down.
Down? Sorry, I was muted.
Yes. Is that right? No, because it says right here, our surface is oriented upward, right? So the only way to make my thumb point up is if my fingers point this way, right?
Okay, yeah.
Does that make sense?
Mhm.
So because my surface has an orientation, which is upward, my curve must be oriented this way to make that orientation work. Okay? And so back to, but did that answer your question?
Yeah.
Okay, so Yosin's question was, why did we choose z equals 0 here? Right? That is 100% by virtue of how the surface was described. And what I mean by that is, it says right here, this paraboloid that is above the xy plane, right? So this description says everything above z equals 0, right? So if this had said something different, like, I'm gonna put a red, this is not what the problem says, but if it did say this instead, above z equals -3, then we would have a different number, right? Then I would put z equals -3 in here. And I get x squared plus y squared equals 4. So that I have a circle of radius 2 instead of circle of radius 1. Right, so the choice of z equals 0 is 100% dependent on the surface that was described. Okay? So I parameterize the boundary curve. And then what we do, we compute r prime, and then evaluate to integral AB FR of t dot R prime of t dt, right? These are just this is literally just follow the directions and put stuff in. Okay, this is nothing sophisticated for you guys to do.
What's the biggest difference between like the curl and the divergence?
They describe different things. The divergence tells us how things are spreading away from a point. Right? The divergence is the sum of the partial derivatives. Right? So the partial derivative with respect to x is how I'm moving in the x direction. The partial derivative with respect to y says how I'm moving in the y direction. The partial derivative with respect to z says how I'm moving in the z direction. The divergence is the sum of the three of them. So the divergence tells us how we're spreading away from any individual points. The curl tells us how we're rotating at a specific point, right? As opposed to moving, I'm just rotating. Curl describes rotation, divergence describes movement away or spread.
Yeah, I asked because like their processes seem pretty similar. It's just that like you use the gradient operator and you cross that with your f for curl, and then you dot it with f for your divergence.
Yeah, well, because divergence is a number. It's a scalar.
Yeah, it's
right?
scalar, yeah.
That's why you take a dot product. The curl is a vector,
Mm.
produces another vector field,
Mm.
right? Because think about like this. At a given point, if I'm going to describe how much I spread away from that point, I can describe that spread with one number, right? But if I'm going to say at a point, I'm going to rotate a certain amount, I need to tell you how quickly I'm rotating and in what direction I'm rotating. Correct?
But can't you describe how far you spread from an object like with direction too? You could. That could be a
You
vector.
could. It could be a vector, but it doesn't need to be a vector. And so, yeah, this is more a philosophical question. It doesn't need to be a vector, right? I have a number that tells me divergence says when this number is bigger, there's more spread. When it's 0, there's less spread, right? Whereas with the curl, with rotation, I actually need
Yeah,
a direction in which I'm rotating, right? If I just give you one number, it's not clear which way I'm rotating, right?
yeah.
Okay.
I feel like just giving us like just looking at it, I kind of feel like to me it makes more sense to leave the divergence as like a almost like a vector, but it's not because you're adding them all up at the end.
Yes.
Oh, yeah, never mind.
Okay. Any other questions? Well, next question.
Question number 5 was also kind of tricky.
Five. Oh, that's the wrong section. 5. 16.8, number 5. I'm going to write this on a new page because that's. XYJ plus x squared y zk. This consists of the top and 4 sides, but not bottom.
Sounds more like a riddle than a question, to be honest.
Of the cube with vertices plus minus 1, plus minus 1, plus minus 1, oriented outward. Okay. So what's the purpose of this discussion of S here? It tells us the surface. So what does this thing look like? Let's try to describe S.
Well, it's a square.
It's a square. It's a cube. Square is 2-dimensional. It's a cube, so it's 3-dimensional, right?
Yeah.
But it's not. It doesn't have the bottom. So imagine I had a square box, right, with no top, and I just put it upside down. That's my surface.
Okay.
Correct? That's why they're saying this: the top and the 4 sides, but not the bottom.
Oh, okay.
Is it sitting directly on the origin?
No,
No.
it's centered at the origin. So its vertices are at plus or minus 1, plus minus 1, plus minus 1. So if I were to try to draw this, which is going to be shitty, by the way, just a heads up. Yeah, this is not going to look nice. Box, shift it down a bit. Its center, the center of the box is at 0, 0, 0. Okay? So it's easier to draw. What is the boundary curve?
A
It's a
box,
square.
It's a square,
square.
right? What is its z value?
In this case, I guess 0, because
Where are the corners of the box? So let's see. This has 8 points, right? The cube has 8 points. Where are the corners of the box? The corners of the box are at -1, -1, -1, -1, 1, 1, 1, -1, 1, -1, -1, 1,
Z is 0. What
one.
are the,
These
1.
-1.
Yeah, it's gonna be a -1 because none of these corner pieces are at 0, right?
okay, yeah.
If I wrote out all the corner pieces, you would see that none of them are at 0, right?
Gotcha.
And the corner pieces that we're talking about are the ones that have z value -1.
Because it's the lowest z value.
Yeah, it's the bottom,
Okay.
right?
Gotcha.
The bottom, not the bottom. So the curve looks like this at z equals -1. Okay? Which way is it oriented?
let's say
This is-
outward?
Yes,
That's fourth. Yeah.
the curve is oriented outward. The surface is oriented outward, yes.
So
Goes to the
it's
right?
outward, and it's counterclockwise, I'm guessing.
Counterclockwise.
Yeah.
Why did we decide counterclockwise?
Because if it was inward, then it would go the other way. Like your thumb would be pointing inside the cube.
Yeah. Okay, that's nice. So we've got this, and what are we trying to evaluate? We want to evaluate the integral over this surface, which we didn't draw, the curl of f ds. But this is equal to the integral over this curve we just drew, right, of f on this curve, right, of dot dr. So do we want to, how would we compute this? We would need 4 parameterizations, right, because these are 4 different curves, and then we compute 4 different integrals.
They're all linear.
They're all linear parameterizations. They're very straightforward parameterizations. We could do it that way. We could check what could we check now though, really quickly.
If it's conservative?
Yeah, we can check if it's conservative, because if it's conservative, what do we get? 0. Why? This is a simple, smooth, closed curve, or piecewise smooth, right?
So if F is conservative, then
If f is conservative, this is 0. And then we don't have to do anything else, right? So how do we check if f is conservative?
First, we have to parameterize it in terms of the. I think.
You had the answer before. Just take the curl.
So, when we were given the initial f, we were given it in terms of like the surface, right? Like,
Well, in terms of 3 space, yes, because it's a vector field in 3 space,
okay,
right? So think of the vector field and the surface as 2 different objects. They're really independent of each other, right? I can make changes to the vector field and I can make changes to the surface. That doesn't matter.
okay,
So I have this vector field. It's right there. It being conservative has nothing to do with the surface at all,
okay.
right? So let's go compute this. Check if it's conservative. How do we check if it's conservative?
Let's do the curl.
We do the curl. So what is the curl?
It's the cross product. Yeah, very good.
Right? So that says that the curl of f is I, j, k, ddx, ddy, ddz of xyz, xy, x squared yz. Okay, so what's the I component of the curl? Did I write that down right?
YZ.
I'm checking to make sure I wrote this problem down right. Okay, I did, yep. Okay,
X squared times Z minus.
okay, let's just compute this here, sorry. So what's the curl? I times x squared z minus 0, right? Minus j times 2yzx minus xy, j. Okay, plus k times y minus xzk. This is the curl. Okay. So we don't get 0, unfortunately. That's fine. So we have to go do this integral. Let's say what that means. F is not conservative. So we need to do the integral. Okay. So how would we do this integral?
Like you said, we could do 4 separate line integrals.
Yep, we could do 4 separate line integrals. To
Is there any
compute
easier way?
this, we could do 4 separate line integrals, or we could just compute
Yeah,
this surface integral, right?
Right?
We already computed the curl,
Yeah.
so
Divide it with DS.
it may not be so difficult, right? And so what is this? Question 3. Okay. So we can compute this with a nice, we can compute this actually. This has a very nice, what am I looking for? Word. I'm looking for a word. You can use an equation in the book. That's what I'm looking right at this equation. It's equation number 3.
Formula?
Formula, yes. But let me think about this for a moment. Oh, okay. Yes, I see the situation here. So this is what I talked about ad nauseum the other day. Right? I said if two surfaces have the same boundary curve, their integrals are the same. Right? That's what Stokes' theorem says. Right? So this is a really sophisticated boundary curve. The surface itself is this box, right? But what's a much easier surface with the same boundary curve?
Square?
A square. Does that make sense? So instead of integrating over this really confusing box like this, its integral of the curl will be the same as the integral of this square in 3 space. Right? So since, let's say, we can define a new surface S1 to be the square with vertices -1, 1, -1, -1, -1, -1, -1, -1, -1, and 1, 1, -1. All right, this gives me the square, a flat square, with z value -1, right? And this surface and this surface have the same boundary, correct? S1 and S have the same boundary. So by Stokes' theorem, the integral of the curl of F on SS is equal to the integral of this curve dot dr. But since they have the same boundary, this is equal to the integral of S1 over the curl of F dot ds. Does that make sense? So we use Stokes' theorem twice here. Stokes' theorem gives us this equality, and it gives us this equality. Right? And this is a much easier surface to integrate over, right? Just a flat square. Right?
This is when you were using the paper and the cup analogy, where S1
Yeah.
and S2 are equal to each other.
Well, no, they're not equal to each other. Their
No.
boundaries are equal to
Or
each other.
bound, sorry.
Yes.
Yeah.
If they're equal to each other, they wouldn't do anything. But their boundaries are equal to each other. One of them is complicated, right? We have this box, 3-dimensional box, essentially. The other one is it's the flat sheet of paper. Right?
Where they connect is
Where they connect is the same. Yeah.
One question.
Yep.
So when we're initially given the question and it
Mhm.
said the boundary is the surface, I don't know why, but I originally thought of it as already a flat square. But how come we're considering three-dimensional surface rather than the flat square to
Here?
begin with? Yes.
Well, this is what they say it is. It's a consists of top and four sides of vertices here. So if I draw, put in place these 3 points, all
Yeah.
these points, there's 8 of them, I'm not going to get a flat surface. I'm going to get a cube.
So when they say surface, they mean like the total surface area of whatever they're describing.
Surface is, what they mean by this is, what we have to do here is draw the points that they told us to draw and then see what shape it makes. That's really it,
Okay.
right?
And whatever the shape is, the vector field is going through that.
Yeah.
Okay.
In this case is the curl of the vector field.
Okay.
So this says that we can compute this thing by computing this thing, which we don't want to compute 4 line integrals, right? We can instead compute 1 surface integral, right? This is a very easy surface to parameterize, right? How do I parameterize this surface? I'm parameterizing the surface that looks like this. R of UV is what?
V.
UI plus VJ minus K.
Y
Okay.
minus K.
Because K is always minus 1.
Yeah.
Right? And 0, no, -1, less than or equal to U, less than or equal to 1, -1, less than or equal to V, less than or equal to 1. Right? This describes the square. And so what direction do I need to point this surface here, S1? Which way is it oriented, up or down?
Up,
Up. Why is it up?
because it's well. Oh, good question.
So we need to make sure that the boundary curve is the same as the boundary curve for S, right?
Okay.
And so if the boundary curve for S is going this way, counterclockwise, the surface needs to point up to make the right-hand rule work, right?
True.
So S is oriented upwards. S1, sorry, is oriented upwards.
So this, even though technically it's like a part of the original cube, we consider it as a completely new.
It's not a
surface.
part of it. Okay. I see the difficulty here. It is part of the cube that was described, but the surface S specifically did not use this part of the cube, right?
Yeah.
It
it's not-
specifically said do not use that,
Okay.
right?
Yeah. True.
So if we were to draw a cube, yes, they're both part of the same cube, but only the top, only the not bottom is taken in S.
Okay.
Okay.
Okay. Gotcha. Yeah. So in this case, like we are saying upwards because it has to follow the same counterclockwise logic to make the Stokes theorem work.
It has to, yes, it needs to have, they need to have the same curve boundary, which means orientation needs to be preserved as well.
Okay.
Right. So let's go back, let's trace that back. S has this boundary, and because S is oriented outward, this curve must be going counterclockwise, right? And since this curve is going counterclockwise, if I want to take the surface that's inside the curve, that must be going upward because this is going counterclockwise. Okay? So this is my parameterization. My normal vector is equal to just the k vector, right? That's the normal, think about, I have a flat sheet of paper and my normal vector is pointing upward. It has length 1. What vector is that? K, right,
Yes.
of length 1.
True.
So when I have a nice flat surface like this, it's really easy to compute the normal vector, right?
Yeah.
It's almost trivial. So now we can compute this integral. Curl of f dot ds, and then we can do this one from basic principles, right? How do we compute the surface integral of a curl of a vector field, right? It's just the vector field. Curl f dot the normal vector, and then du dv.
Yeah.
Right? The normal vector is pretty easy for us here, which is just k. So we're going to take the curl and dot it with k. So that means we take just the k vector of the curl. Dx dy. Change this to x's and y's. Minus 1, minus 1, 1, 1. Y minus xz dx dy. Z is equal to minus 1. So we get y plus x dx dy. Okay. Did that make sense?
Yeah.
That was a lot of stuff going on.
So when we the R thing,
Parameterize?
yeah, parameterize it. How do we utilize that information?
It's right here.
So we only did that to find where U and V are bounded, how U and V are bounded.
Well, we did it to do two things. Because we did it to do two things, but one, the bounds, but also I'm going to write this like this so they're a little bit easier to understand here. We did. Remember in this example, we did f of r of t.
Yes.
We're still doing that right here. But in this case, r of t are trivial, right? X becomes x and y becomes y. So nothing changes.
Okay.
And we have the bounds. So we did this step as well,
Okay.
but we didn't need to make any changes.
Gotcha.
Okay? Does that make sense? Okay. Any other questions? You've all been very quiet today, most of you.
So if you were to prepare for this final exam, what would you study?
Okay, that's something I guess I should talk to you about. The first, think about, okay, don't know who that is. Think about the course as a whole. The last couple sections really heavily relied on things you already knew, right? Like dot product, cross product, vector stuff. You for sure need to know that. But will I ever test you on compute the cross product of these two vectors? Probably not, because that's not a useful, that's useful only because you need to do it in other places, right? So you should know how to do those things because we use it right here, right? We use the dot product right here. So I would not go and study sections, 12 and 13 and 14 even, maybe. I would understand the concept from 14, but I would not practice computing partial derivatives because you already need to compute partial derivatives in all the other sections, right?
Yeah.
So if this were me, I'm not saying this is the best way to study. There's no best way to study. But if this were me, I would study all the problems in the later sections that rely on the other sections as materials, right? Because chapter 15 is multiple integrals. Stokes' theorem and things sets up multiple integrals, right? Of course, go and remember your polar coordinates and your cylindrical coordinates and your spherical coordinates, because those are tools that may appear that you may need, okay?
Okay,
So-
thank you.
Those are my thoughts. Take them for whatever you want. They're not the gospel or anything. I haven't even written this exam yet, so I really can't tell you. But I am going to be very sure, very certain that the question, compute the dot product or compute the cross product, is never going to be there. Okay? You should know how to compute, planes through certain points and tangent planes and stuff, because that's necessary, because you need to talk about tangent planes and things like that. And you need to know how to parameterize things. I'm not going to ask you to parameterize this ever. But if you do a problem on Stokes' theorem, you need to know how to parameterize, right? Or else you can't do these problems.
Question.
Mhm.
So as you spoke about the tangent planes, what did we use them for? I just can't remember, like application-wise, like how we do with the partial derivatives and whatnot in Stokes' theorem and Green's theorem and stuff.
So tangent planes were used for approximation, right?
Oh yeah.
Because when a
Optimization.
function is when we have a really complicated function, but we know as tangent plane, we can approximate the function with the tangent plane, right? We use tangent planes to compute surface integrals, right?
Okay, yeah.
Because tangent plane gave us a way to compute the normal vector, right?
Yeah.
Because how do we compute a normal vector? We got to find the tangent plane and then find the vector that's normal to that tangent plane, right?
Yeah.
That's how we computed normal vectors. So conceptually, they're pretty useful. They are conceptually equivalent to the derivative, right? The derivative is very useful. It tells us how the thing is changing, right? The tangent plane tells us how the surface is moving. Yeah, so from the earlier sections, really remember the concepts from the earlier sections. The computation, which I'm sure you can already do, because you've been doing them this whole semester. Okay? Any other questions? So I'm going to put up these notes after class and this video. I'm going to remind myself to do it before I go to work, because usually I tell myself I'm going to do it, and then I go to work and I forget to do it. So I'm going to do it. If I don't get these up to you, if I don't send you an email by 3:30 that says all the videos and notes are uploaded, someone send me an email and remind me to do it. Okay?
Can you send me an email to remind you to do that?
I'm going to send you well, there's 5 of you guys now, so you guys should be able to keep me accountable. Hopefully. So, are there more math classes here at the college after this course?
Say that again?
Are there more math classes at the college after this course?
Only
Yeah.
discrete.
Yeah. Yeah, I think this, and I think DBQs is before this.
Differential equations.
I have a question about fundamental theorem of line integrals.
Uh-huh.
So whenever I do these questions, I kind of get confused just by the like the process of trying to find the gradient of f such that it equals your function.
No. So you got that backwards, but
So
you
I
said
did
it
wrong.
backwards. I don't know if you're thinking about it backwards, but you said it backwards. What you should be saying is trying to find the function such that the gradient of that function is my vector field.
So I wrote it down backwards. That's why. But so usually you'll have some, it says like find the potential for,
Mhm.
and it'll give you some vector valued function. You usually what I do is like there's like the step-by-step process that you go through, and usually it's you take your
Do you
first
have
value.
a problem in mind? We'll just do it and then we'll walk through the process.
Sure, I can just like pick one, or do you want me to read one off to you?
Sure. Or pick one, or read one off. I don't know.
Um,
Either way, I'm gonna write it down.
okay. I'll do the one I just did. So it is the function is f equals
Capital F?
y, huh? Yeah, big F. Y equals, or yeah, so y times e to the x.
How many variables does this have?
Just two, x and y.
F of x, y is
So yeah, y e to the x plus sine y. That's the I value. And then plus e to the x plus x cosine y j.
okay.
And I found the answer, but it was just like trying to make a step-by-step process on what you
Okay.
do. That was kind of
So-
confusing.
So if this is conservative, right, we're saying we claim this is a conservative vector field, and we want to find the f such that this happens, right? So we want f of x, y such that the gradient of f equals f, right? That's what we want to do. So how do we check if this f exists?
If it exists,
Yes. How do we know it exists? Because if it doesn't exist and we keep looking, it's going to be
oh, you can by proving it's conservative. Is that the whole
yes.
point?
How do we prove it's conservative?
So
Oh,
I took
we take the derivative of q with respect to x and minus the derivative of p respect to y, I think, and then see if those are equal.
Yep. We don't need a minus sign if we're going to see set them equal.
Yeah,
but
sorry, yeah.
Yeah. Does the derivative of this with respect to y equal the derivative of this with respect to x? Right. So that's what we should be doing. Correct. Alternatively, we can take the curl of this vector field, and we should also get 0. Right. With the addition that 0k is in my vector field, if we wanted to take the curl, because that way we have one sort of technique for all of them. Okay, so check it's conservative. I'm going to tell you right now, if you try any of these techniques without it being conservative, you're going to have a bad time. Okay, because then you're going to be looking for a solution that doesn't exist. So whenever you're looking for potential fields, make sure it's conservative to actually have one. Okay, that's the step 0. Check it's conservative. Okay, I'm going to put the steps over here, and then our solution will go here. So now I have this thing, and I want to find a function f that has this as gradient, right? So I know that this is the derivative with respect to x, right? If gradient of f equals f of x, if the gradient of f equals capital F, then this right here is its derivative with respect to x, right? So that says that y e to the x plus sine y is equal to partial of f with respect to x, right? So what can I do here?
you can integrate.
Integrate with respect to x, right? So integrate, and I get f is the integral of this with respect to x, which is y e to the x, plus this with respect to x, sine yx, plus some function that has to do with y only, right? Because when I take the derivative, this goes away, right? Now I can take the derivative, and I get derivative of f with respect to y is e to the x plus cosine of y x plus g prime of y, right? And what is this equal to?
You compare that to the j component of your.
Yep, to q over here. So that says that e to the x plus x cosine of y is equal to e to the x plus cosine of y x plus g prime of y. What does that tell us?
G prime of y is 0.
G prime of y is 0 equals 0. So what does that tell us about g prime, about g of y? This implies that g of y is
Y.
1? Or
It's
what
Y.
functions have derivative equal to 0?
an infinite
wait,
amount?
Constant.
An infinite number of
Constants.
them, but what kinds of functions?
Linear ones?
Not true. Only some linear functions.
Let me just pick constant.
Yeah, constant.
Constant functions, right? So we could integrate this with respect to y and we get a constant, right? Is some constant.
Yeah.
And what constant do I want to pick? Doesn't really matter what constant I pick,
Yeah.
but I can pick any of them. I might as well pick 0, right? So okay equals 0 is good, right? So our function looks like this. F is y e to the x plus sine yx plus 0.
Wouldn't it be plus k? Or
It could be plus k, but we just said I can pick any one.
Any,
It doesn't
sorry.
matter which one I pick.
I was
The
listening.
constant doesn't matter at all. So I might as well pick the easiest constant, 0. Okay. So let's put these steps down here. What do? We check conservative. This is very important. Please do not forget to do this. Your life will be miserable if you look for one function and it's not conservative. One, and this part right here this is not the only way to do this. This is the way that we've chosen, right? We could have started with Q as opposed to P, right? So integrate P with respect to X, right? That's what we did right here. Differentiate to find F.
Integrate.
Differentiate F with respect to Y, right? Equate the two and get an equation for the function g of y. Sorry, g prime of y equals stuff for integrate the equation to find g of y. Then substitute g of y found in 4 into g of y in 1. Okay. This is not the only way to do this, but this is the method we just followed.
So I did a lot of problems similar to this one. And so a lot of other ones had some sort of Z component to them. That changes this, well, it doesn't change the process, but it adds more to it.
Yes, it changes the process by adding things to it. It doesn't change what we're doing. We're doing the exact same thing, right? Instead of, so here, if we have a Z component, our G function has two variables now in it, right?
Yeah.
A X, a Y, and a Z. We're gonna do this to find a G with respect to Y. And we're gonna integrate that. And then we're gonna differentiate with respect to Z. So we're doing the exact same thing. If we have more variables, we just do steps 2 through 4 twice.
Twice, yeah. So for this, quite literally this example, say it hadn't been 0K, it had been like XYK or something. Your G it would have been GY.
Well, G is never gonna have X in it in this case. Because G is a function of Y only.
Then maybe, I don't mean that. I mean, like, if your Z component, like K, had been, I don't know, maybe say ZY.
Yeah, so you mean if this K was non-zero,
Yeah.
then yes, we would have to check that as well. And then if this was non-zero, then G wouldn't be G of Y, it'd be G of YZ, right? And then I take the derivative, and this is, instead of the derivative of G, it's the partial of G with respect to Y, right? This is Z here.
Z.
And then so on. We follow this through and we do it again for this part of the function.
Okay.
Right. So remember, if we have more variables, we're just doing this again for we're doing steps 2 through 4 again for each extra variable we have. Okay. And theoretically, we could find this for some number of variables, any large number of variables, right? But